In this video, I will talk about the total probability theorem, which is an extension of the concept of conditional probability. In conditional probabilities, we take a subset of the sample space and compute probabilities within this subset, hoping that that yields a simpler computation. In the total probability theorem, we extend this concept to multiple subsets and try to compute probabilities of events that span more than one subset of the sample space. Since this is so closely connected to conditional probability, I strongly recommend that you have this as a prerequisite before watching this video. If that concept is not familiar to you, I have a video on conditional probabilities on this YouTube channel. Before introducing the total probability theorem, as usual, I'll give this motivational problem that we'll solve before the end of the video. So here we're considering a factory that has 3 machines which produce robots. The machines produce the same type of robot, but they are not equal. Some of the machines are able to make more robots, and they make them with higher accuracy, such that there are fewer defects on the other side. So machine A, B, and C make 25, 35, and 40% of the robots respectively. So C is making way more robots than machine A. Additionally, when these machines make a robot, they have a 5%, 4%, and 2% probability of producing a defective robot. So in addition to being faster, machine C also has higher accuracy in making correct robots. Unfortunately, the quality control at this factory is terrible, or actually it's completely non-existent, because they just sell all robots, regardless of whether or not they have a defect. The question is then, if you buy a robot from the factory, what is the probability that it's going to be defective? Now, if you're up to the task, I can recommend you to try to solve this problem without being familiar with the total probability theorem. It is possible that you can intuit the solution on your own. If you can't solve it, or if you get stuck, then please continue and learn about this total probability theorem. Okay, so let's introduce the total probability theorem. As you can see in the text here, we're considering multiple events, and we're considering that these events are mutually exclusive. So what does mutually exclusive mean? As you can see in this beautiful illustration on the left, we have 2 different scenarios. In the top scenario, the events A1, A2, and A3 are all mutually exclusive since there's no overlap between these events. So it's never possible that you draw a sample and that 2 different events hold for this sample. However, in the bottom picture, we see that events are not mutually exclusive because there is a region that is in common for event A1 and A2. Therefore, it's possible to draw a sample in this sample space and have more than one event being true. So in this second scenario, the total probability theorem will not hold. In other words, when you define your events, you need to make sure that they are mutually exclusive. Secondly, we need it to be true that these events fill the sample space completely. This is actually true in both of these examples, since there's no part of omega here that is not covered by one of the A events. Given that these 2 conditions are true, we have this equation here. So this equation is really the statement of the theorem. And what the equation says is that any event B, so B you can draw as you like. It can be within one of these A, it can cover all of them, or just a subset of them. Any event B can be computed by taking this sum here on the right. And if you look at the terms of this sum, you see that first we're always taking the probability of this subset of the sample space. So what we're doing there is really restricting ourselves to this subset. Then once we have restricted ourselves to that subset, we compute the probability of event B given that that subset is true. So if you think back to the concept of conditional probability, essentially what each term in this sum represents, it is this part of B here that is exactly inside this subset. So for instance, A1 here, we would have this shape here would be the first term. So we restrict ourselves to A1, which means that we discard everything here in A2 and A3, and then we compute the probability of B within this subset. So that would be this slice here. Then what this statement says is simply that if you repeat this for all of these different events E and take the sum of these probabilities, those sums will exactly equal the probability B, which should be intuitively correct looking at this figure right here. Now, what I like to do when I see a new theorem like this is to perform some very simple computation where I already know the answer, just to validate in my own mind that this is actually correct. So let me do that now. Let's consider that we're rolling a die, and therefore the sample space omega is just all of the 6 outcomes that we can get on the die. So we have something like this for our sample space omega. Then let's define these subsets A that are both mutually exclusive and fill the sample space completely. So we can say, for example, that A1 is the subset of rolling a 4 or lower. So it would contain these. And then the event A2 here could be that we roll 5 or higher. Now, clearly, these two events are mutually exclusive, and they cover the entire sample space together. Then we define some event B that we're interested in computing. Let's say that this event B is that we roll either a 4 or a 5. Okay, so now we have all of the events we need. Then what does this theorem say? Well, the probability of B is just the probability that we roll 4 or 5. And this should be immediately obvious that there's a 1 in 3 chance that we roll one of these two numbers. But let's validate this by computing this using the theorem. So the theorem tells us that the probability of B is the probability of A1 multiplied by the probability of B given A1. And then we just do the same thing for A2. We can do something like this. I don't want to write it out. Now, what are these probabilities? Well, the probability of A1 is 2/3, because 2/3 of all values are represented here. And if we know that we are within event A1, then what is the probability that event B occurs? Well, event B has the number 4 in it, but not 1, 2, or 3. So one of these 4 events mean that B occurred. So this is a 1 in 4 chance. Similarly, for A2, we have a 1 in 3 chance of getting A2. And if we get A2, there's a 1 in 2 chance that we get event B. So in total, this is 1/6. This is 1/6. 1/6 plus 1/6 is 1/3, as we expected up here. So hopefully this gives you at least some idea and some intuition of what this theorem and that it is actually correct. Okay, so at this point, we have introduced the total probability theorem, and we're now ready to solve this factory problem. If you didn't pause the video at the start, I strongly recommend you to pause now and try to solve this problem yourself. But without further ado, I'll introduce my own solution to this problem. So as you remember from the definition of the total probability theorem, we have 2 conditions that need to be true. First of all, when we divide our sample space into these subspaces, then we need these subspaces to be mutually exclusive. In other words, that there's no overlap in these subspaces. And secondly, we need to make sure that these subspaces completely cover our sample space, such that it's impossible to draw a sample that is not part of one of these subspaces that we define. So let's illustrate this here, right? So let's say that this circle is the omega, which is all robots that are being produced. Then this subspace can be split into these 3 machines. So first, machine A makes 25% of the robots. So that's just 1/4 of this circle, right? This is A. Then B makes 35, so it's slightly more, maybe something like this is B. And C is the biggest one, that's making 40% of the robots. Then we have this defect. So a defect is possible in all 3 machines, so it should be somewhere here in the middle, but it's more likely for A and slightly less for B and much less for C. So maybe it looks something like this, where A is quite big, B is going to be slightly smaller, and then C is going to be very small. Maybe something like that. And we're interested in this probability D, we can call it. So the probability of having a defect. Okay, this is the essential setup where we can now split the space into these three subsets and then compute the probability in each individual subset. But we'll do that in the next slide. So at this point, we have our three events defined, and we've already checked that the conditions for the total probability theorem hold. So first of all, their intersection is the null set, or in other words, they are mutually exclusive. And additionally, if we compute the union of the events, we recover the entire sample space. So this means that when we're looking for the probability of a defect, we can indeed split this computation down into three different parts and then do those individually. So the theorem tells us that the probability of a defect is going to be the probability of machine A making the robot multiplied by the probability of a defect if it was indeed machine A that made the robot. And we're going to do the same thing for machine B and machine C. And at this point, it should be quite clear to you that this problem was defined with the total probability theorem in mind, because all of these 6 probabilities that we want to compute are directly given in the problem. So what is the probability that machine A made the robot? Well, it's a 25% chance. What is the probability that it was a defect? Well, if machine A made it, it was a 5% chance. And we can go on like this. So this is machine B. And then we have the superior machine, machine C, the machine we all want to be, right? And I computed this ahead of time. This is 3.45% chance of being a defect. So if we look at these probabilities, this does intuitively make sense, right? Because there's more robots made by machine C, and machine C has a lower probability of error. So we would expect this to kind of pull down the average probability by quite a bit. However, together, A and B make up 60% of all the robots, and their average error is 4.5. So we should be somewhere between 2% and 4.5, and we should be slightly closer to 4.5 than we should be to 2, which is also what we see here in this answer. Okay. If you're interested in learning more about probability theory, I can recommend you to check out Bayes' theorem. This is a very famous theorem that I think sometimes you hear about even if you're not a probability theorist, because there's a big debate in the statistics community whether you should be a Bayesian or a frequentist statistician, essentially. So that might be something interesting to check out. And at this point, you have all the prerequisite knowledge to learn about Bayes' theorem. Secondly, the reason that I chose to teach this total probability theorem is actually because I had a particular problem in mind. So there is a famous problem within probability theorem, a very classical problem, called the Russian Roulette problem. I'm planning to make a video on this next. It's a substantially harder problem than the kinds of problems I've solved in my earlier videos, so it will be a video completely dedicated to just solving the problem itself. But at this point, if you watch my videos, you know everything required to solve this problem, so you could already give it a go yourself. I'm planning to make 10 more videos, next one on this problem, but I'm also going to make more after that. And finally, I want to say that these videos are very inspired by this book by Gunnar Blom. And if you want to learn more, I can heavily recommend buying this book and reading it.